Hello, we're back again with our continuation of our series of lectures on rational functions, rational relations, rational expressions. So in our last video we mainly talked about what we meant by a rational relation, a rational expression actually, and we compared that to rational numbers. We talked about some basic things about rational numbers, particularly about how to reduce fractions and how to multiply and divide fractions. And then we saw that we can take exactly those same algorithms and to do those same things for polynomial fractions, which are rational expressions. Be able to multiply and divide rational expressions, be able to reduce rational expressions, be able to factor polynomials, find the greatest common factor and least common multiple. Now, once we're familiar with factors, multiples, least common multiple, greatest common factor, then we can really talk about fraction operations. And we've talked about, conceptually probably the harder one is multiplying and dividing fractions, but to actually compute the algorithm, it's actually easier than adding and subtracting fractions. So when we add and subtract fractions, let's look at a picture here. So here we see, on the left we see two fractions. The one whole square, that area represents 1, and it's very important when you're talking about fractions that you're talking about fractions of the same thing when you're talking about adding or subtracting or multiplying or dividing them. So here we're talking about a fraction of a square. So 1 is a consistent amount. So we can see that the blue shaded is 3/5 of that one whole square. What have we done? We've divided that square into 5 equal pieces and shaded 3 of them. That's what the fraction 3/5 means. Similarly, the red shaded here is 1/4. Now we can simply take the red part here, kind of flip it over and stick it up here with the blue, or flip the blue over and stick it down here with the red. But the question then that would be adding it, but the question would be, what fraction does that make of the whole? Certainly it's 3/5 plus 1/4, but can we write that as one single fraction? And the problem is, to write something as a fraction, you have to have it divided up into equal sized pieces, and the blue pieces and the red pieces aren't the same size. So the way to make them the same size is to break them up into even smaller pieces. So very purposefully, notice I've divided the blue one up with vertical strips and the red one with horizontal strips. And so if we take the horizontal division and put it on top of the vertical division and vice versa, we see a total divisions there of, well, what is it? It's actually 3 times 5. It's 5 times 4. Okay, 4 rows and 5 columns. So that's actually 20 divisions. And if you notice, when we've done that, we actually get 12 of them shaded blue, and down here 5 shaded red. Well, now that they're the same size, we can simply take the blue ones and move them down here with the red and shade in, and we get this picture at the end, which is a total of 17. And so notice what we've done is we've taken numerator 1 times denominator 2 plus numerator 2 times denominator 1 and divided by the product of the denominators. Now sometimes when you're doing this, you can you don't have to, we can always do it by just multiplying the two denominators, but in constants that may work out just fine for us, but in polynomials, when we apply this, we really need to get our hands on the least common multiple for the denominator to get our least common denominator, which is why we went over least common multiples earlier. So here you can see what we've done here to make these equivalent fractions. So we took 3/5, wrote it as multiply top and bottom by 4 to get 12/20ths. Take 1/4, multiply by 5/5 to get 5/20ths. Now they're the same denominator. Keep that and add the numerators to get 17/20ths. So this is going to allow us to go to adding and subtracting fractions. And we have some steps here. Let's look at some examples. So here's our original problem here, 4/15 plus 5/6 minus 2/9. So you're going to factor each denominator into prime numbers. Leave the numerators alone. So 15 is 3 times 5, 6 is 2 times 3, 9 is 3 squared. Now find the least common multiple of all the denominators. Okay, so again, how do we do that? Well, if you have them in prime factorization form, it's pretty easy. You just take all the bases you see, put them in increasing order, and use the highest power you see for the power. So we see 2 to the first power, we see a 3 to the first, 3 to the first, 3 to the second, so we're going to go with 3 to the second, 5 to the first is all we need. And so it's the same denominator in all three cases. So the question is, what do we multiply by to bump the denominator up? Well, we already have the 3 and the 5, we need the other 3 and the 2. So that's what's going to go in this second part right here. The first part here in the numerator is the first parentheses is the original numerator. And the second one we're going to multiply. We've got a 2 and a 3. We already have a 2 and a 3. We need the other 3 and the 5. So what's down here that's not up here is what goes in the second parentheses. Same way here. We have both the 3's. We need the 2 and the 5 down here. So we need the 2 and the 5 in there. And that's the next step, is to go ahead and put those in, or the completion of the next of the step we're on. Now go ahead and multiply out the top. 2 times 3 is 6 times 4 is 24. 3 times 5 is 75, and 2 times 2 times 5 is 20. Now they all have the same denominator, so I rewrite it as one fraction with the same denominator and add or subtract in the numerator. And of course actually do the addition and subtraction in the numerator as indicated. That's 79. Now notice I've left the denominator factored. This is better because the next step is I want to reduce it, and to reduce it I want to factor the numerator and denominator. Turns out 79 is prime in this case, so we can just leave it like it is. Nothing cancels, so we can see it's reduced. Finally, in the case of constants, we want to go ahead and multiply out the denominator, which is 90 in this case. Alright, now, so those are the steps. Okay, so let's look at this example here on the left. To make this a little bit bigger, we can see it. 7/12 plus 5/9 minus 4/75. Recopy the numerators, recopy the minuses and pluses, but factor the denominators. 12 is 2 squared times 3, 9 is 3 squared, 75 is 3 times 5 squared. Get a common denominator. 2, the biggest power we see on that's 2, the biggest power on 3 is 2, and the biggest power on 5 is squared. So it's the same denominator all the way across. What's in the denominator here that's not here? The other 3 and both the 5's. So what are we doing going from here to here? We're multiplying top and bottom by 3 times 5 squared. The next one here, what's down here that's not there? The 2 squared and the 5. So what are we doing from here to here? We're multiplying top and bottom by 2 squared times 5 squared. I don't care what that is multiplied out at this point. I want to just leave it factored. Next one here, what's down here that's not here? Well, it's the 2 square and one of the 3's. So 2 square and 3, so we're multiplying top and bottom by 2 square times 3. Our fundamental equivalence property of fractions allows us to do that. Now go ahead and multiply out the numerators. 7 times 3 times 5 squared is 525. 5 times 2 squared times 5 squared is 500. 4 times 2 squared times 3 is 48. Notice the first parentheses in the top is the original numerator up here. The second parentheses contains what's in the denominator that's not in the original denominator. What's in the common denominator that's not in the original. So now notice we have a common denominator, so we can rewrite it as one fraction. We're going to add or subtract in the numerator to get 977. Factor that and cancel. Actually, really only factoring you have to do is make sure that it doesn't have any 2's, 3's, or 5's. And I think that's actually prime, so we work that out. B, another example of the same thing. Now, let's go over here at C. C is now, so that was arithmetic. That's elementary school stuff. Now let's do some intermediate algebra stuff where we actually add this together with fractions. So it's exactly the same steps. What's the first step? Recopy the numerators and the pluses and minuses as needed, and then the denominators, factor them. So x squared plus 3x plus 2 factors as x plus 2 times x minus x plus 1. X squared plus 4x plus 4 factors as x plus 2 squared. Then multiply the top and bottom of each fraction by something to get us to have a common denominator. So find the least common denominator, that is the least common multiple of the denominators. How do you do that? Take all the factors you see for bases, prime factor bases, prime polynomial factor bases, and keep the same, the largest power you see. So again, you want to write these as don't write this as x plus 2 times x plus 2. Think of it as x plus 2 squared, and then you can use this little rule. So the x plus 2 you can see is going to be a power 2, and the x plus 1 is power 1. How do we get from here to here? Well, we already have the x plus 2 and the x plus 1. It's the second x plus 2 we don't have, so that's what we multiplied the top and bottom by. So that's what we have there. In the other one, we need the x plus 1 to multiply the top and bottom by to make an equivalent fraction with the same denominator. Now, leave the bottom factored, multiply out the top. So in the numerator, x plus 3 times x plus 2 is x squared plus 5x plus 6, and x minus 5 times x plus 1 is x squared minus 4x minus 5. If there's a minus here, then we need to distribute. Here we're going to put them together and combine like terms. X squared plus x squared is 2x squared, 5x minus 4x is x, 6 minus 5 is 1. Factor that. That turns out to be prime, at least over the natural numbers. And so there's nothing we can do to cancel. If that would factor and cancel, then you would do that next. Okay, more examples of the same. Here's one with addition and subtraction. Still not any real harder, just longer. Okay, and I'll let you look at that to see that later. More practice, some with just constants, some with variables. These first two for sure you should be able to do without a calculator at all. Even the third one, it takes a little while to factor that down, but just peel off a factor at a time and you can get it down even without a calculator. Now let's look at compound fractions. Compound fractions are fractions inside of fractions. So the one technique there's actually a couple of techniques you can use here, but one technique that works really nicely is to factor all the little denominators inside. So 16 is 2 to the 4th, 12 is 2 squared times 3, 18 is 2 times 3 squared, and if you want to think of that as 6 over 1, you can. Now, look at the little denominators, 2 to the 4th, 2 squared times 3, 2 times 3 squared, and then 1, and put all the prime numbers that you have for bases there, the highest power you see. So in other words, find the least common multiple of all those little denominators. Multiply the top and bottom of the big fraction by that. Now when I distribute, I will be rid of my little fractions inside of fractions. So when I distribute in the top, the 2 to the 4th cancels, leave me 3 times this 3 square. So 3 times 3 square, that's 27. And then the next one, the 2 of the 2's cancel and 1 of the 3's, so it leaves me a 2 squared times 3 times my original negative 5, gives me negative 60. In the bottom, 1 of the 2's and both of the 3's cancel, leave me a 2 cubed times the 11, which is 88. And here, there's nothing canceled, so it's just negative 6 times that whole thing, which is 864. Now go ahead and do your subtractions, or additions, in this case, subtractions. We get negative 33 over negative 776. Factor it. If it's negative, we're going to factor out a negative 1, and by the way, both those negative 1's cancel. 33 is 3 times 11, 776 is 2 cubed times 97. Nothing else is going to cancel except for the negatives. So in the end, we see the reduced fraction version is 33 over 776. Now guess what? When we do it with polynomial fractions, in other words rational expressions, the steps are exactly the same. The algorithm is exactly the same. The only difference is when it comes to multiplying things, you're multiplying polynomials. When it comes to adding or subtracting things, you're adding polynomials. When it comes to factoring things, you're factoring polynomials. But it works the same algorithm. So factor the little denominators. X squared minus 4 is x plus 2 times x minus 2. X squared plus 4x plus 4 is x plus 2 squared. These down here are prime polynomials, so I just put parentheses around them. So get a common denominator of all the little denominators. Notice that we'll have an x plus 2 squared and an x minus 2. Least common multiple of all the denominators is that, and that's what we multiply by the top and bottom of the fraction, and this is going to, when we distribute, it's going to get rid of our fractions inside of fractions. So the first time when we distribute here, the x minus 2 cancels and one of the x plus 2's cancels, so that leaves us 3 times x plus 2. In the second part we have our negative 2 times, well, the x plus 2's cancel, both of them, and you got x minus 2. This one, one of the x, well, the x minus 2 cancels, so we get x plus 2 squared times our 5. And the next one, one of the x plus 2's cancel, but we still have the other x plus 2 and the x minus 2 times our negative 2. Now, multiply out, distribute 3x plus 6, negative 2x plus 4. Square this first. Actually, you know what I did here? So I'm going to ultimately need it factored, so I noticed I had an x plus 2 in common. And so I factored that out. But there should not be a 5. If that carried all the way to the answer. Yeah. So we factor out an x plus 2 and we're left with 5 times x plus 2. And here we take an x plus 2 out and we got negative 2 times x minus 2. Distribute, that's 5x plus 10 and negative 2x plus 4. 5x minus 2x is 3x, 10 plus 4 is 14. And so we get x plus 10 over x plus 2 times 3x plus 14. None of those factor anymore. No canceling going on, so there's your reduced version. By the way, notice when we had constants, we had a tendency to multiply out those prime factorizations to get it to a single number in the numerator and denominator. When we have polynomials, we leave it factored. So there's actually one step less in the algorithm here. We don't want to multiply it out. We'd rather have it factored. So, more examples for you to try here. And we'll talk about, actually, you know what, I'm going to do this now. We're going to talk about equations with fractions. When you're solving equations with fractions, we use a technique similar to that used on compound fractions. We'll factor each denominator, compute the least common multiple of the denominators, and multiply both sides by the least common denominator, or least common multiple of the denominators, and then expand out the multiplication using distributive property as needed. And at this point you should have no fractions, so they should be cleared out. And then we can proceed as usual. Okay? The only thing you have to be really careful of is if you multiply both sides by 0, then the whole thing doesn't work. So there is a possibility you can introduce what are called extraneous roots here. So you have to check, at least check enough to make sure that you didn't multiply by 0. Okay? So let's look at an example here. This one factors as x plus 2 times x plus 1. This one factors as x plus 2 times x plus 4. And this one factors as x plus 1 times x plus 4. Then the next one, so now find a common denominator all the way across, which is x plus 2, x plus 1, x plus 4. When I distribute on the left, notice that the x plus 2 and the x plus 1 cancel, leave me x plus 4 times 2. And here the x plus 2 and the x plus 4 cancel, leave me x plus 1 times 3. On the right, the x plus 1 and x plus 4 cancel, leave me x plus 2 times 7. Distribute now. So now the fractions are gone. So that's the nice part. Now distribute, you get 2x plus 8, 3x plus 3, 7x plus 14. Now we're pretty easy from here on out. Combine like terms, subtract, let's see, that's not right. So I'm subtracting 7x from both sides. Actually, let's do it this way. We'll subtract 5x from both sides, and then subtract 11 from both sides. Okay, and so if I do that, then what happens? No, subtract 14 from both sides. Okay, if I do that, that gives me a negative 3 on the left, and it gives me 2x on the right. So I had it right here, just didn't have that part there. Divide both sides by 2, and we get x is negative 3/2. Now, you have to make sure that that doesn't make the denominator 0. The things that make the denominator 0 are negative 2, negative 1, and negative 4. It's not one of those. So if we didn't make any mistakes, it should check. But of course, it's always a good idea to check it. Now, of course, that's the calculator. That's the way to do it. But you can also do it as a calculator let the left side be y1 and the right side be y2 and see where those graphs intersect. Or get 0 on one side and then whatever you got left on the other side, let that be y1 and see where it crosses the x-intercept. You can also do it that way if you have calculator technology. Okay, so we'll start there talking about rational functions. Now that we've reviewed rational expressions, we'll start talking about the college algebra material, which is rational functions, on our next video.